So instead of the two variables both going up together like they do with a direct variation, for an inverse variation, one variable goes up, the other partner variable goes the opposite direction, going down. That's why it's called an inverse variation. So we're going to explore that, and we're going to actually, it's very soon here in the lesson, we're going to talk about some examples, and the most famous one that's going to have an inverse variation is the law of gravitation. So I'm actually going to introduce and show you the law of gravity that has some direct variation and also some inverse variation, so you can understand how we use this stuff in the real world. So let's recall for just a second, because direct variation and inverse, they're kind of like peanut butter and jelly. They go together. So we're going to recall the direct variation. And we did this extensively. If you haven't looked at that, you probably should go back and look at that before getting too far down the road here. Now, we said in the last lesson that the concept of direct variation always really has the same form. Some variable is related to some other variable in a direct fashion with what we call a constant of variation. That was the variable m. Now, I like to use the letter m when we were talking about direct variation because it was basically a line. We talked about this. This looks like a line that goes through the origin. But I also told you that oftentimes in books, you'll see it written like this. Y is equal to k times x. It's exactly the same equation. Here we're saying the constant of variation is m. Here we're saying the constant of variation is something called k. It's exactly the same thing, and this is often used as well. Now, what we mean here is that for this type of direct variation, if you did a plot of y and x, it would be a line that goes directly through the origin. The slope of this line is going to govern how y and x are related to one another. And so the slope of the line determines how fast y goes up whenever x goes up. And so we call that a direct variation. And it's a line that goes basically through the origin like that. What it basically means is that when the x variable goes up, the y variable also goes up. So if x goes up, y also goes up. Now we need to contrast that with what we're going to learn today, which is just as important, and it's called inverse variation. Just like I gave examples of direct variation in that lesson, there are many examples of inverse variation in real life. Everything from gravitation, we'll talk about it today, to electricity, magnetism. I can go on and on. Any branch of science or engineering or math has inverse variation type of relationships you can find. So whereas direct looks like something like this, y is equal to k times x, inverse variation looks like this. Y is equal to k divided by x. Right? So look, first of all, at how these things are related to one another. This one is a direct variation. As x increases, y must also then increase. How much does y increase? Well, it depends on what k is. If k is 100, then y will go up a pretty large amount compared to x. If y is 25 million, then of course, as y is going to go up a whole lot more, and the slope of this line will be very steep. For inverse variation, it has all the same parts. You have y and x that are related to one another through a constant of variation. So we say that the constant variation is right here, the constant of variation. All right. And whereas before we would say y varies directly as x, we did that in the last lesson, what we would say here is y varies inversely as x. Right? So this word inversely tells you something very important. What does it tell you? It tells me that whenever I look at this guy, if the x variable increases, if this denominator of this fraction goes bigger, let's make it 100, let's make it 1,000, let's make it 25 million, let's make it 75 million, then I'm dividing by a bigger and bigger number, so the y variable then has to be forced down, right? So that means that when x goes up, the y variable goes down in the opposite direction. That's why we call it an inverse variation. If you flip it around the other way and say, what happens if the x variable goes down, then what am I doing here? This variable goes down, let's make it 10. Let's make it 5. Let's make it 1. Let's make it 0.01. Let's make it 0.000000001. You see, when I'm dividing by a really small number, then that makes the y variable get really big. So no matter what x is doing, if x is going up, y is going down. If x is going down, y is going up. How much does y respond to the change in x? Well, that depends on the constant of variation, which we call k. if k is bigger or smaller, is going to affect exactly how much y responds in relation to x. But no matter what, if it has this form, you can see from the equation that y always has to go in the opposite direction of x from what we just talked about here. Now I'm going to do a more detailed plot in just a second. But a lot of students think that an equation like this, y is equal to k over x. They know that it kind of looks like this one, and if this one is a straight line like this, then they think, well, maybe it's a straight line that looks like this. And you kind of trick yourself into thinking that this is a straight line that goes in the opposite direction. This, in fact, I'm going to put it in big letters so you don't get confused here. This is not true. The shape of this thing does not look like this. Let me show you what it does look like, and then we're going to do a more detailed plot here in just a minute. An inverse variation looks like this. If this is x, and this is y is equal to some k divided by x, then the shape of this curve looks something like this. It has a curve to it. Notice it does start high over here, and it does end low over here, but it is not a straight line that goes between these points. It goes down, and it bends over, and it goes something like this. And if you think about it, it actually makes sense that it cannot be a straight line, because if you think about it, let's look at a regular equation of a line that we know. Let's say that y is equal to 2x plus 1. We know what this guy looks like. 2x plus 1 means that we have a y-intercept over here at 1 somewhere, right? And the slope is positive. So I'm not going to do rise over run, but you know you rise 2 and you run 1 or something like that. So you know this line's going to look something like this. Of course, I could continue my axes or whatever, but you know it's going to go in a positive sense like this. All right? What is going to happen if you try to take a line, I'm running out of space here, if you try to take a line that goes in the opposite sense, that slopes negatively, what would something like that look like? That would be something like y is equal to negative 2x plus whatever y-intercept it is, 3 or whatever. I'm just making it up. It doesn't really matter. What I'm trying to say is that we know what the equation of a line looks like when it's slanted this way. It looks like the regular equation of a line, it's just the slope is negative. So the y-intercept is going to govern where the thing crosses, and the negative slope is going to make it slant this way. So a lot of students will look at this equation in the moment, and they'll think, well, this one slants like this way, then this one's going to slant this way. But you know that this cannot be the equation of a line. It can't be the equation of a line, because in this equation, the x is not on the bottom. It's not downstairs. We know what equations of a line look like when they slant like this. It's mx plus b, but m is just negative. So I'm showing you without proving to you that it cannot be, that this equation cannot be a line slanted in the opposite direction. In fact, it actually looks like this. It's not a straight line at all. It bends, and it does go from a high value to a low value, but it bends over like that. All right? So I want to give you a concrete example as to what an inverse variation really is, something that you can wrap your brain around. I'm going to talk about gravity in a few minutes, but before we get to that, I want you to think about speed. You're driving down the road in a car or a bicycle, whatever you want. Let's say you're going 10 kilometers. That's the distance of your journey from your house to your school, let's say. And it's 10 kilometers, right? And you want to figure out what the speed is. You know, kilometers per second or kilometers per hour. You know, it's distance divided by time. That's what speed is, right? So if you're driving down the road, if you travel 10 kilometers, this is the fixed distance. It doesn't change. Then the speed here is distance divided by time, but the distance I already gave you. It's just a 10 kilometers, right? 10 kilometers. And I have to divide it by the time. Now, a lot of times we talk about hours, but let's talk about it in terms of seconds. So this is going to be kilometers per second. So it's distance divided by time. So in other words, the speed s is going to be equal to 10 divided by some time t. And you see what happens here? This equation for the speed that you're traveling to the grocery store or whatever is inversely related to the time. It has exactly the same form of this. There's a number on the top, which is the constant of variation. There's a variable on one side of the equal sign, and there's a variable on the downstairs underneath the number. And what this means here is that as the speed increases, or I should say, let's do it this way. As the time increases, in other words, as it takes you long time, let's say it takes you 6 hours to make that journey. You convert that to seconds, really long time. you must be traveling really slow. If it takes me 6 hours to get there, then I must be walking really, really slow. So as the time it takes goes very, very high, that means that my speed must have been really, really low. Let's take the alternative. Let's say that it takes me hardly any time at all. My time, as I decrease the time, let's say it only takes me 6 seconds to make that journey. Like maybe I'm fire a bullet or going on a super fast rocket or something like that. It only takes me 6 seconds. If I go 10 kilometers in 6 seconds, that means I must be traveling really, really fast. So as the time goes down, that must mean that the speed has gone up. Why is that the case? Because you see what happens here, if I put a really big number for the time in here, I divide by a big number and I get a small number over here. So that's what this means. If I put a really small number in here, tiny, let's make it half a second or something, then I'm dividing by a small number and my speed goes really, really fast. So whereas in direct variation, everything is on the same level here, as the x goes up, the y goes up. But for the inverse variation, as the x goes up, the y goes down. As the x goes down, the y goes up. And that's why it's called inversely related to one another. Inversely, you don't use the word proportional. You say they're inversely, they vary inversely with respect to one another. Okay? Now what I want to do is I want to get a little more detail as to the shape of this curve. Right here I told you, hey, the shape of this curve looks like a bent over, kind of like a bent line, kind of. It's not a line at all. But I want to talk to you a little bit more about where that shape of that line comes from. So let's talk about our example where we have the speed is equal to the distance divided by the time. Right? So we said that the speed here that we're calculating, we're only going 10 kilometers. It's 10 kilometers divided by the time in seconds, right? So let's make a table. So let's say if a journey takes, we're going to make a little table of values here. Let's say it takes 1 second, 2 seconds, 3 seconds, 4 seconds, or 5 seconds. Like this. Then we want to calculate the speed. The speed is equal to 10 kilometers divided by however long the thing took. All right, so we're going to go ahead and calculate this. So the speed is 10 divided by the 1 second. So this is 10, and it depends on your, I guess I did kilometers, and let's do seconds. So this would be kilometers per second. That's a speed, right? Kilometers per second. Doesn't matter what the units are, but whatever. S here for this guy, I still went 10 kilometers, but it took me 2 seconds. So it took me longer, right? And so when I take 10 divided by 2, it actually takes me 5 kilometers, or my velocity, my speed turns into 5 kilometers per second. Notice that the speed is actually half because it took me twice as long to go that distance. So that makes sense. Now if it takes me even longer, 3 seconds, 10 kilometers divided by 3 seconds, and I have to stick that in a calculator, I'm going to get 3.33, I'm rounding here, kilometers per second. And then if I go and do 4 seconds, you see the pattern. 10 divided by 4, you're going to get exactly 2.5 kilometers per second. And at 5 seconds, what you're going to get is 2 kilometers per, kilometers per second. So you can see what happens that as the time goes up, here, right here, the time goes up. Then what happens here is the speed goes down. But it doesn't go down in a line. You might think it's a line because of what we talked about earlier, but it doesn't go down in a line. So we need to actually draw a plot of this to show you what it really looks like. So this is not going to be exact, but it's going to be enough to get the point across. So this is the, I'm plotting the speed, and this is the time. All right, so now we need some tick marks. We have points, right? So I'm going to go, notice I went from 1 to 5 seconds. So I'll say 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. So I'll say 1, 2, 3, 4, 5 seconds. And my speed went from 2 to 10. So I'll do something like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so now I have enough information. And of course, the distance between the tick marks isn't quite the same, but it's still going to show me basically what I'm trying to find. And that is that if it takes me 1 second to go on this journey, then my speed must be 10. So 1, 10. That's what I'm going to plot for the first point. 2 comma 5. If I'm plotting a speed versus time, kind of a relationship between the two variables, 2 seconds would be 5 kilometers per second, which it cuts it in half, which is right around here. 3 comma 3.33. So here's 1, 2, 3, and I'm going to go just a little bit up from that. I'm trying to get 3.33. It's not exact. 4 comma 2.5. This is 1, 2. 2.5 is going to be somewhere around this. And then 5 comma 2, 5 comma, here's number 2 right down here. So you can see clearly this is not a straight line. And if you were to connect it with a smooth curve, I'm not going to probably do the best job freehand, but you can see what's basically going on here. That's not too bad. It goes something like this. So basically the curve gets really, really close to the axis, but it never really touches it. And it gets really close to the axis over here, and it never really touches it. Because if I put a time of 0 in here, 0, if literally the journey took 0 seconds, if I'm going 10 kilometers, it took me 0 seconds. You divide by 0, it's like you've got infinity speed. You can't really ever get there in 0 seconds, so it's like infinity speed, so the speed's like off the chart. And if it takes me 100 million years in terms of seconds, then the speed is going to basically be 0, or so close to 0. That's why it gets close to 0 this direction. But this is what the curve looks like. This curve here, it does go from high to low as time goes on, but it is not a straight line. We know what the equation of a line looks like. This is not the equation of a line. This is actually what we call a hyperbola, and we're going to study hyperbolas in the next unit of algebra here, where we talk about conic sections. It's a very special curve called a hyperbola. But in this case, I just want you to know that the shape of the inverse variation goes down like this in this smooth fashion. Now, what I want to do for the rest of the lesson is I want to pause the idea of the inverse variation, and I want to talk to you about something which we call joint variation. And then we're going to talk a little bit about gravity, because gravity is a good equation that has example of direct variation along with inverse variation. And then we'll call it a day and we'll solve some problems. So the final thing I want to talk to you about, let me see, where am I going to do it? Yeah, I'm going to do it right here. I want to talk to you about, actually I want to do it over here. I want to talk to you about what we call joint variation. Don't worry, it's very easy to understand. We just have a new word for it. But basically what it is, joint variation happens is when we have variation, or varies, directly as the product of 2 or more variables. Let me give you a couple of examples of that. Let's say that I gave you the equation S, whatever S is equal to some constant of variation times x times y squared. Now, if the y squared wasn't there and it was just k times x, you would say that k varies directly as x, right? And that's correct. So k does vary directly as x, because as x gets bigger, then s also gets bigger. Now, if I were to cover up, I'll put my thumb over it. If I cover up just the x part, you would say s varies directly as y squared. Now, this does not mean that s and y vary directly. You can see that y has a square on it. But still, the y squared is sitting over here next to this constant here, and it's multiplied. So the relationship between s and x is direct, and the relationship with s and y squared as an entire term, if you want, I can put little parentheses around it, as an entire term is a direct relationship too. The relationship between s and just the variable y, of course, is a square variation. But if I look at the entire term, the whole thing, it varies directly as s. When you have two things that vary directly and they're multiplied together, you call it a joint variation. So you say that s varies jointly as x and the square of y. So it does not vary directly as x and directly as y, because we have a square there. It varies directly, or jointly I should say, as x and the square of y. Another thing you might want to say is you could say s is jointly proportional to x and y squared. So same sort of thing. So a lot of this stuff is terminology. When you have a joint variation, it just means you have a direct variation between two different things. We have a direct variation between s and x. We have another direct variation between s and the quantity y squared. But since they're all together in the numerator and they're multiplied, we say that we have a joint variation. Joint variation means it varies directly as the product of two or more variables. So we have a joint variation between x and y squared. So we've talked about direct variation, we've talked about inverse variation, and now we've talked about joint variation, which is basically just direct variation with two or more variables, right? So now I want to give you an example of when you have an equation that can have a direct variation and an inverse variation in the same equation. And the most famous example I can give you of that is the law of gravitation. The law of gravity. Now, what I should say is this is Newton's law of gravitation. So we're going to write the equation on the board. Newton's law of gravity is accurate enough for most uses in everyday life. We used Newton's law of gravity to send the astronauts to the moon, to calculate the trajectory to go to the moon. It's accurate enough for almost anything we're going to do around the neighborhood of the Earth and the Sun. However, we now know that Einstein's theory of gravity is more accurate and it's much more complicated than Newton's theory. But for most purposes, the law of gravitation Newton came up with is perfectly fine. So we're just going to talk about this one, even though we know Einstein's theory of gravity is a little more accurate than this. So the law of gravity says the force that exists between two objects is going to be something we call the gravitational constant, right? Times the mass of body number one times the mass of body number two, because you have to have two things to attract each other. So this is the mass of body number one, the mass of body number two. And you're going to divide that by the distance between them, but the distance between them squared. Now I'm going to draw a picture and I'm going to show you what this means in just a second. But I want you to realize that this g out here is just a number. This g out here is exactly the same thing when we have y is equal to kx or y is equal to k over x. It's just a constant of variation. It's a number that Newton calculated based on, based on his theory, based on his experiment. So for the purpose of this class, I'm going to rename this g. I'm going to rename it k, right? And so it's m1 times m2 divided by r squared. And just to make it even more clear, I'm going to basically write it one final way and say that it's k. I'm going to bring this k and I'm going to bring it upstairs because it's k over 1. I can multiply that times that fraction. So it's k times m1 times m2 all divided by r squared. So it's a little easier for us to see what's going on. I'm just moving the k upstairs here. This is the law of gravity. I mean, just think about what you're looking at. This is like hundreds of years of people wondering what happens. How is the moon going around us and all this, how does it work? This equation describes the force between any two objects in the universe. It describes the force between you and the door. It describes the force between the sun and the earth. It describes the force between this marker and my nose. It describes the force between a proton and an elephant. It describes the force between any two objects. All you have to know is the masses of the two objects, and you have to know the distance between those two objects, right? So for instance, if I was going to do this in terms of the Earth and the Sun, I would say, well, okay, I have a sun here, and then way far away I have a smaller ball, and this is going to be called the Earth. In reality, the sun is way bigger than the Earth, so this is not really to scale. But the distance between these guys, we're just going to call it r. It's just the distance, how many meters it is the sun is away from the Earth. That's all it is. And the sun, of course, has some mass, and we're going to call it the mass of the sun. Now that could be m1. I'm going to relabel it ms because it's the mass of the sun. And we could call this the mass of the Earth, so that could be m2 in this equation. So then if I was going to calculate, the force between the sun and the Earth, all I would really do is I would say, well, the force between these things is this constant of variation. It's a gravitational constant times the mass of the sun times the mass of the Earth in kilograms. Literally, if you could weigh it in so many, trillion kilograms or whatever it is, the sun and the Earth, you'd put those numbers in and you would divide not by r, you would divide by r squared. So you would figure out how many million meters it was. I have to go look up the number. I know it's 93 million miles away, but convert that to meters, it's going to be a bigger number. You would square that and you would divide the gravitational constant times the masses and divide by this guy. So notice what you have here. Wrapped up in all of this stuff, as the mass of the sun increases. In other words, let's say the mass gets bigger, 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 bigger. Then this number, if everything else is the same, this number getting bigger, bigger, bigger is going to mean that the numerator is bigger, 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 which means the force has to be bigger. So you see how, because it's in the numerator, as it gets larger, it makes the force go larger, and this is what we called a direct variation. So we say that the force, the gravitational force, is varies directly as the mass of the sun. And we can also see from this equation that as the mass of the Earth increases, we can also see that the force also increases because it also lives upstairs. So if we make the Earth bigger, 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 and everything else we hold constant, like we leave everything else alone, then the force must be bigger. And that is what we call a direct variation, right? Now remember, we just said a joint variation is when things vary directly as the product of two or more variables. So forget about the bottom here. Two or more variables, it seems that that's what's happening. We have direct variation, two or more variables. So these two on the top we call joint variation. It's just a label. It means we have two or more direct variations, that's all. And then finally, to bring it home, let's look at the bottom. As this radius, or the distance between the sun and the Earth goes up, if I make this distance bigger, 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 if I make everything farther and farther apart, you would expect the gravitational force to go down. And it does. Because if this number gets bigger, I'm dividing by a large, large number, which makes this go down. So the force then goes down. This means that we have an opposite direction of the movement of everything, and we call this inverse variation. So I wanted to bring it home. Let me make sure I caught everything on my previous notes here. So what we basically figured out is that we've used the very famous law of gravitation to really bring what we're learning, down to earth, so to speak, to show that it actually has a practical relationship. We know that the gravitational force between, I did the sun and the Earth here, but between any two objects varies directly as the mass of object number one. It also varies directly as the mass of object number two. And it varies inversely as the square of the radius. And it turns out that this inverse variation thing, it happens for gravity. It also happens for electricity and magnetism. The electromagnetic force also is an inverse square kind of distance kind of relationship. There's lots of examples in nature when you have direct variation and you also have inverse variation. Of course, this is not just a straight inverse. It's an r squared. So it's a little more steep of a drop off because you're not just having the thing in the bottom. You're having the thing in the bottom square. But it's still an inverse relationship. So bottom line, direct variation means increase variable A, then variable B also goes up. Inverse means increase variable A, the other variable then goes down. We looked at the shape of the curves. We've looked at an example from real life, from physics, but I could pull examples from any branch of science. And so you should now know that inverse and direct variation are basically part of our something that we need to learn because it exists in the real world. Now in the next lesson, we're going to solve some more problems. This was more of a lesson here, and then we're going to solve some problems with inverse variation. So make sure you understand this. Follow me on to the next lesson, and we'll conquer a few problems with inverse variation. Learn anything at mathandscience.com.